So this talk will be about evaluation strategies, and as the foundations in the title may suggest, there will be a few theorems in the talk, and it will also feature a lot of lambdas. But I guess no one should be afraid of this, because we all know here that lambda calculus and functional programming, that's basically the same thing. So this little riddle should be easy for all of you. What is the result of this lambda term in the middle? I'll give you just a few seconds to make a bet. The point is that this might be one of the simplest questions I know of in the lambda calculus, because basically any answer you can think of might be correct. Depending on whether you are thinking in terms of functional programming and, for instance, call by via value, you could have answered the term on the upper left corner, which is a value. Or if you are more the call by need kind of programmer, then the answer on the bottom left corner is also what the theory could tell you. And if you are thinking in terms of lambda calculus, then maybe you had thought of the last one on the bottom right corner, which is the actual normal form of the term. The bottom line here is that we have here a separation between two slightly different worlds, which are functional programming, which corresponds to weak reduction in the lambda calculus, that is, evaluate a term, literally evaluate, reduce until you get a value, and then once you get a value, stopped. You are not interested by what is inside. And strong reduction, which is the actual semantics of lambda calculus, which is reduce all that can be done in the term until you get a normal form. The consequence of this is that if you are working with a tool that is actually using lambda calculus, the real lambda calculus, not just functional programming, then maybe the usual techniques of functional programming are not enough for your needs. And that's the point of this talk. Giving an extension of the usual call by need that works well with the actual semantics of the lambda calculus that goes to a normal form. And this might be what you want, for instance, in the proof assistance, when you have to implement this kind of complete reduction. So here is the program of the talk. So don't be afraid. That's pretty much like any outline of any talk. Just yet, you do not understand half of it, but it will become pretty clear as we move along. I will just hide this colored part under a letter V because we do not really need it for now. And we can try to explore what I call the weak call by need strategy. That's usual call by need. I'm just labeling it as weak, not to confuse it with a strong strategy we will define. So that's a strategy, probably that's the favorite evaluation strategies of several people in the room. And there have been many works in this community around this notion of call by need and laziness, both before and after this paper I'm pointing out. This is just one of the fundamental papers in the field, and I'm just picking this one because it will serve as a reference to ensure that our extension of call by need is actually related to some usual official definition of call by need. And the nice thing is that this beginning of the first page contains the main two ideas of call by need for which we'll start, which will be that here, first idea is that in lazy evaluation or in call by need, we only reduce an argument if the value of the corresponding formal parameter is needed for the evaluation of the procedure of the body. And second part, which is memorization, which is at this point, is that after reducing the arguments, the evaluator will remember the resulting value for future references. So let's start. Here is a program. The program I showed you at the beginning. And first thing is that the shape of the term, that's an application of a function to some argument. What call by need says that we should not prematurely evaluate the argument because we don't know yet if it will be needed. So we just create a binding between the variable x and the actual argument. And this can be done, for instance, with a let construct. In this talk, we'll just use a slightly more compact explicit substitution notation. That's exactly the same thing from a semantical point of view. That's that t in which x is substituted by u, that's the same as let x equals u in t. So now we come with a term in which we have an application of a left part on a right part. We still do not want to evaluate the right part because that might be an argument which is or not needed. So we start by evaluating the left part, and this can be formalized by a notion of evaluation context that dive on the left of applications. So here on the left, we have this lambda y x applied to omega, which is a standard, the same kind of regex we had just before. We apply the same rule. And we arrive at a point where then the value x is needed. So we need its value. We can evaluate the argument that was bound to this value. So there is another kind of evaluation context that says exactly this, and that allows us to evaluate the argument. So we can do this. And in the end, what we get is that x is bound to something which is a variable z itself bound to something which is a value. It's a lambda. So this time, we can substitute the value and we can go on with the computation. So the second reduction rule tells us exactly this. Now, so that's the core of call by need, but it's not, actually it's not enough. Quite soon, actually, just the next step, you find another problem, which is you are in a case in which x is bound to a value, but not exactly a value, that's a value and a substitution. So we need some way to move the substitutions around to be able to go on with evaluation. And in the call by need lambda calculus paper, they propose a rule for this. We just move the substitutions, and then we can apply the usual rules for substitution. Actually, a close inspection of this standard call by need strategy shows that this rule that allows to move the explicit substitutions is used only in this very precise case. So what we propose here is to merge the two rules of substitutions and moving applying the substitution and moving the substitutions to get this only one rule which combines the two behaviors, the actual computation and the bookkeeping of the bindings. And the very same phenomenon appears with the beta rule. So here I have the function applied to an argument x, just there is a substitution in between, so we have the same kind of rule, administrative rule that allows to move the substitution, and then we can apply the rule. And same thing, we take only one rule, which is a combination of this. And so with this, we arrive at the actual result of call by need evaluation for this term, which is a value v. It was a lambda b something, so that's a value under some context of substitutions. And this was defined using two reduction rules and a few rules for context, for evaluation under context. But this v, it's a value, okay, but there is still some computation that can be performed inside the value. So that's not an actual normal form in the lambda calculus. So that's what we'll be doing next. Now we'll try to extend this strategy to go to the actual normal form of the term. And for this, we will have two constraints. That's a decent choice. That's two constraints we chose them on purpose. The first one is a conservativity theorem over the actual call by need strategy. That is, whenever the usual call by need strategy is doing a reduction step, our strong strategy will perform exactly the same reduction step. And so only in the cases where the usual strategy does not say anything, then we we might invent something new to go on with computation. The second theorem we want is a theorem of completeness with respect to beta reduction. That is, as soon as your lambda term admits a normal form, then the strategy will find it. Even if there are some ways of diverging, the strategy will not fall in this kind of trap. So let's go back to our program, just update it to the new part. So I expanded the V part, and I also shrink some parts of the ending substitutions, which will not be that useful for the rest of the talk. And so the V is a lambda abstraction with something inside. And since we have to evaluate it, this lambda abstraction, it is not like the previous one we have seen. It is not applied to anything. That is, it will never be used in the usual way. So if we want to compute what is inside, we have to do it now in some way. We have to force it. So we can use an additional context rule that say, okay, we can go under lambdas. But obviously, we cannot do this in any unconstrained way, because we already knew a few cases in which we do not want to do that. For instance, if your lambda abstraction is already on the left of an application, then weak call-binding strategy tells you that you are supposed to be doing beta reduction at this point. So we should not go under the lambda if you want to be conservative. And that's the same with the substitutions, right? So our solution for this is to split, is to have another version of evaluation context, which is a strict subset of the general evaluation context. But in this evaluation context of the strict subset will be the only one allowed in some places. That is, take two arbitrary evaluation contexts. You cannot compose them and get an evaluation context. Maybe at some point you have some structure to obey. And this will be one of the tricks we need to do this. Second one is, well, we'll see it. We'll try to reason on what we can do on this term. So we are going on, we are evaluating under the lambda B, and then we have an application of a term B on a term CA. So the rule for now is, on an application, first evaluate on the left, because maybe on the right that's an argument that is not needed. So first, the left. Okay, the left, that's B. What is B? B is the variable that is bound by the lambda abstraction. So usually what we'll do is that, well, let's try to evaluate B. If the abstraction is applied, then B will be substituted by something, and we'll want to know what this something is. But wait, if we are here under the lambdas, that means that this lambda abstraction is not going to be applied to anything. So this B will never be substituted by anything. It can be considered as a constant. Okay, so what can we do with this? The first thing that we have some notion of constant variable, or as we call them, frozen variables, which depends on the context in which you are. So the evaluation context become tagged with some indication of what is frozen at some point. And then what do we do? If this is a constant, it will not turn into a function. It will not be applied. And as a result, this gives some notion of structures. We are defining a part of the term which is stable. That is, forever it will be, if we have a x frozen applied to some terms t1, t1, forever it will be x applied to some terms t prime 1, t prime n. So this is a stable structure that we call a structure, and then we can go on evaluating the arguments of the structure. That's the only case where we allow evaluation on the right of an application. Well, frozen variable, that's even a little bit more complex than that, because other subtle situations in which we can indicate that some variable are frozen. Consider this case here, right? We have, so that's the term we just had. So we already know B is frozen. So since it's frozen, we are evaluating on the right part, which is CA. We start evaluating on the left, which is C. C is bound to some term, to variable D in a context. And D is bound to B, which is frozen. So B will never be substituted by anything. That means that D also will never be a value. So all this part can be considered as a structure, as something which is frozen, which means that C itself is frozen for another reason which is slightly distinct of B. So next, the next step would be evaluate right of the constructor C, evaluate A. So A, and then we can go on. A, it's bound to X, and X is bound to something in the context, which are hidden. So just a splash to a summary of all the rules we had for defining evaluation context. And now I'll just give a few words on the completeness theorem. So completeness theorem, that's something which is well, infamously difficult in such context. And I just want to give you a few words about it because we have a technique which is quite new to this and which helps a lot in having a tractable proof. So the statement of theorem is that if there is a normal form, then the strategy will reduce the term to some term which is related to the normal form. And we proceed in two steps. First step is based on a typing argument on intersection types and say that if our term is normalizable in the lambda calculus, then it will be typable in our fancy type systems. And then from the typing derivation, we'll be able to derive a reduction sequence that uses the reduction rules of call by need. And this reduction sequence will go to a normal form. So that's not yet exactly a strategy because we are using the rules of call by need, but maybe not, sometimes not in the valid evaluation context. So there is a second part which is more syntactic inversion of reduction steps that will allow us to complete the proof and make the links between what you have extracted from the typing argument and the actual reduction in the strategy. And so what is special about this intersection types is that it's some kind of resource-aware semantics. Here's the typing rules for application, and what we can see is that it features not a sigma to tau functional type, but a multi-set of types to tau, with one type for each potential use of the variable. Which means that if your variable will never be used, actually you do not need to type the argument. So that's not a problem if the argument is diverging. But in building on this, we can elaborate the argument and get the proof I just described. Go take a look in the paper to have more details on this. So finally, what we had here is the definition of a strong call by need strategy, which is an extension of the already known call by need strategy, but which is complete with respect to lambda calculus. And while we also have developed an abstract machine, it's not in the paper, but well, it should come in some time. Thank you.